Hi, my name is Salvador Alvarez. I'm a senior manager in the product planning group focusing on AI solutions. And today I'll be talking about unlocking the full potential of FPGAs for real time machine learning inference. In today's discussion, I'll be using ASR or automatic speech recognition to illustrate how an overlay can unlock the true potential of an FPGA based platform for AI inferencing. An end-to-end conversational AI engagement starts with taking the audio of what somebody spoke and transcribing that into text. That's called speech to text, or ASR, or speech transcription. The next flow in the conversational AI engagement is to take those words that the person spoke and pass them to a natural language processing model. That model is responsible for understanding what was said and generating a response. Then, the last part of the simplest AI engagement is to take that response and synthesize that into sound. And that's called text to speech or speech synthesis, so that the speaker can then get their response from the AI conversation. Typical ASR models, which we'll be focused on today, are connectionist temporal classification, listen, attend, spell, and recurrent neural network transducers. When you're speaking to a person or an AI model, the AI model must meet certain requirements. First of all, just as when you're talking to a person, you need to get a response in a very quick time. Try talking to someone and waiting 3 seconds before you respond to anything they say. They will very quickly get annoyed speaking to you. And for ASR, the, the target is to have a latency of 10 milliseconds or less. Similarly, when a person is talking to anyone, whether that's AI or a person, they also want to be well understood. And for that, that means you need to have a low word error rate. And the target for ASR is to be within 10% of human level performance. Aside from just the expectations a person will have, there's other system requirements. In these times of chip shortages and high energy costs, and a focus on environmental, social, and corporate governance, efficiency is really key. Running inference on the most efficient platform improves all of these metrics significantly. And finally, we've seen just how rapidly the field of AI and machine learning has evolved in less than a decade. New, more powerful models are constantly being developed all the time. And so we need a platform that is flexible enough to run those new models without having to change the hardware. In the past, one way is to simply throw more servers at the problem. And for simple machine learning models and low throughput, this is probably still an acceptable solution. But as the use of machine learning increases and models become larger and far more complex, that's no longer appropriate. Simple plug-in accelerators, which are far more suited to run those specific tasks of AI inferencing, can dramatically reduce cost, power, real estate, and most critically in this case, also latency. The workloads are offloaded to these accelerators by the host CPU, resulting in a very large increase in performance and throughput. Data accelerators can be based on GPUs, ASICs, or FPGAs. Let's compare these options. CPUs have been around the longest and were developed to be able to run any workload. However, because they can run any workload, they don't run any workload particularly well or efficiently. On the flip side, you have ASICs, and they are the most efficient device to perform a specific workload. However, the development time and the cost are extremely high, and the resulting device lacks that flexibility to implement a wide range of current or future workloads. GPUs have been developed to blend that performance and flexibility, and they've done a pretty good job at it. However, particularly when low and deterministic latency is required, FPGAs can do better. Besides conversational AI, there are many other real-time applications that require that low latency, including financial trading, security, defense, and so on. When we look at the marketplace, there is a wide range of FPGAs architectures available today. But let's look at specifically what's required for machine learning. AI inference requires high-intensity multiply accumulate functions with lots of data stored in quickly accessible memory. Let's take a look at each one of these requirements. First, early FPGAs were simply arrays of lookup tables and flip-flops, and these were the simplest logic functions on which all other functions were built upon. Later on, hardened multiply accumulate or MAC blocks were added, making them very proficient at digital signal processing functions. And in the latest round of FPGA families, you now find those hardened MAC units have developed into a highly efficient processing block for machine learning, especially with the addition of embedded memory. Machine learning inference workloads are compute intensive, so we need a lot of these ML processing blocks available. Second, we need high bandwidth memory, and we need this in two places. First of all, the embedded RAM in the MLP blocks are critical for fast compute, but it's not possible to make it large enough to store all the weights in the model. The weights are stored in DDR memory off chip, and we need a high-speed interface to access those weights quickly. But even once we get the data into the chip, whether it's the output of compute functions or bringing in data from the external DDR, we need to be able to move that data quickly within that chip from the interface to the MLP block or an MLP block to another MLP block. For this, a purpose-built network on chip can ensure data transfer is both fast and deterministic. And lastly, we need support for various numerical precisions. Although machine learning training is usually done at floating point 32-bit precision, when it comes to inference, there are more suitable formats. Quantization is widely used in AI inference to achieve much higher performance since the alternative formats require fewer bits and dramatically simplify both the compute requirements and reduce the amount of memory required, which also in turn enables faster memory access. And very often, quantization has been shown to have a negligible effect on the accuracy of inference, especially when we're talking about 16 bits. Even when you go down to int8 for precision, you're often able to recapture some of the accuracy loss by retraining or doing quantized aware training. But on top of that, there's even a lot of evidence that block floating point formats, such as BFP16, as supported by the Speedster, can be used in post-training with negligible loss of accuracy, but with the compute efficiency approximating equivalent that of int8. And with that, I'd like to introduce the Speedster 7T, which has the FPGA adaptability with the ASIC performance. This chip is built on the TSMC 7 nanometer process technology. And the key points are that the MLP blocks are able to perform over 80 TOPS, and they support block floating point, and int formats. We also have a GDDR6 that's capable of transferring data at 4 terabits per second, so we can get those weights quickly into the chip. And we have a 2D NOC capable of transferring data at over 20 terabits per second, so we can move that data quickly within the chip once it's there. We also support PCIe and Ethernet interfaces. To take advantage of that chip, let's talk now about the overlay. For most software developers and machine learning data scientists, designing an FPGA is out of the question because it requires specialized hardware design skills, and a good understanding of FPGA architectures. To make FPGAs accessible to these communities, the design interface needs to be abstracted to a much higher level. And an overlay makes this possible. An overlay can optimally configure the hardware on an FPGA to create a highly efficient AI inference engine, yet leaving it software programmable. A good overlay will utilize a high percentage of the features on the FPGA and enable the design to be clocked at or near the maximum specified rate. On the top right, you can see an example of an overlay implemented on the Acronix Speedster 1500 FPGA. This floor plan shows 4 cores, each placed and routed into its own quadrant. The cores shown here are the MAL Accelerator cores from our partner company, Myrtle.ai. And below you can see the block diagram for that core. The matrix vector multiplication are performed in the MLP blocks using the 16-bit floating point precision. As you have seen, these are natively supported in the Speedster 7T. Since these blocks are hardened, the MLPs are able to be clocked up to 750 megahertz, whereas the functions implemented in the more flexible LUTs cannot be clocked as fast. To get the highest throughput from the device, the MAL accelerator clocks the MLPs at twice the rate of the LUTs. So the overlay combines expertise from machine learning, from hardware design, and from software design to get the most out of the FPGA. That means that a retrained model, or even a new version of the model, can be run on the FPGA without changing the hardware configuration at all, because it also includes because it's also runtime configurable and software programmable. This enables ASIC-like performance with CPU-like flexibility. Machine learning programmers can still design their models using the popular frameworks they're used to today, such as PyTorch or Caffe2, etc. An overlay would typically be delivered with a complete acceleration stack, which includes a bitstream for the FPGA, drivers, and an efficient host API to facilitate simple integration into existing service provisions. This completely abstracts the user interface from much more above the hardware design, making the benefits of FPGAs accessible to all. So continuing with what we saw in the last slide, here's how we can turn that optimized FPGA with its overlay into an ASR product. The FPGA and the memory used for storage are housed in a PCIe Gen 4 accelerator card, operating under 250 watts. This can be plugged straight into any suitable server. The FPGA is configured with an RNN-T model for the ASR, and it's already pre-trained with over 100,000 hours of English language data. Of course, it can be trained on other languages, and it can support multiple languages simultaneously. The appliance has a very low and deterministic latency, which enables it to be used for real-time conversational AI. It can process thousands of voice streams simultaneously, and that's up to 20x higher than a CPU running without FPGA acceleration. The server CPU controls the ASR appliance, offloading the ASR workloads to the card. Being software programmable, the ASR appliance can actually also be used for other functions besides ASR. So here we return back to the concept of using a data accelerator instead of multiple servers to manage increasing demand for more voice channels. In this case, you can achieve the same throughput as one server with one PCI accelerator card than you would need with 20 of the same servers. That's a difference of approximately 10x in capital costs and energy consumption, and potentially 20x savings in rack space requirements. So let's look at what people are generally doing today. Generally, the most common solution that people use for ASR is to use a cloud service. These cloud service providers can charge anywhere from 1 cent to 2.5 cents a minute. Aside from limiting the latency with cloud solutions, there are other reasons why you would want an on premise solution. First is security. Many industries, such as medical, financial, or governmental agencies, are sensitive to limit their risks and want to avoid those risks associated with cloud services. Second is cost. The cost of these online providers can add up for various enterprises, and we'll look at a case study in the next slide. And lastly, many of the cloud providers are off the shelf solutions. You may have a specific use target you may want to improve the performance on, and may even have your own data set to improve that performance. Some examples include supporting for another language, but it can also be technical jargon in a specific industry or field, or even accents in a language, such as Spanish accents in English, for example. So let's take a look at a case study on cost and put aside the security and customization aspects for now. If we take a look at a large enterprise that's handling, say, 50,000 calls a day, with the average call duration being 5 minutes, then your annual cost is anywhere from $500,000 to $2 million a year. Alternatively, the enterprise could achieve the same capability on site using the Achronix ASR appliance. And factoring in both the capital expenditures and the operating expenditures, the same cost for that same capacity would only be $100,000. That's a factor of anywhere between 5x and 20x lower, depending on what you were able to negotiate on pricing with your online provider. That's a cost reduction of anywhere between 80% and 95%. Let me take a step back and just show you the offerings that we have here at Achronix. We have 3 form factors where we offer data acceleration. First is our most advanced high performance FPGAs called with the Speedster 7T, which is optimized for data acceleration. We also provide embedded FPGAs or eFPGAs, which is an IP that you can integrate inside your SoC or ASIC, which is great for workloads that may change slightly over time. You don't have to redevelop an ASIC, you can reprogram the eFPGA portion to take advantage of the updated workload. And lastly, we have accelerator cards, such as the one of our ASR Appliance, which is a high performance PCIe data accelerator. All of these offerings are fully supported by our Achronix ACE design tools, which include synthesis verification, timing, programming, and debugging. So let me summarize today's discussion. We focused on ASR, which is the first stage of the conversational AI pipeline. FPGAs are ideally suited to accelerate those low latency applications, those real-time applications, such as ASR for real-time streams. Achronix and Myrtle.ai are developing an ASR platform that supports more than 1,000 real-time streams on a single 250-watt PCIe accelerator card. And the Achronix ASR appliance on one x86 server can displace up to 20 servers running the same deep learning algorithm. And most importantly, we can reduce your first year CapEx and OpEx up to 90% for ASR. So if you'd like to learn more and get started with us, please feel free to visit our website or contact any of us here at Achronix. We'll be happy to help and talk to you more. Thank you very much for your time today.